as we do electrolytic cells or electrolysis, it's still a lot of the same ideas. As we said, anode oxidation, cathode reduction, electrons flowing from anode to cathode. We have a fat cat in general, the cathode getting fatter. We still do our calculation of cell potential the same way, and we're still going to be looking at our standard reduction potentials. But sometimes we have some different scenarios. So the most simple of electrolysis is where you just have one pure substance and therefore only have one option of what can be oxidized and reduced. A good or a classic example of that is melted, molten NaCl. So that means I don't have my solid salt, but most importantly, I don't have salt water. I have sodium ions and chloride ions that are freely moving around and melted, not dissolved. So if we look at this, we could see, well, we've got this right here. So we could think about what needs to be oxidized and what needs to be reduced. But what's really important with electrolysis, probably more so than with galvanic and voltaic cells, is thinking about what is actually in the cell. The sodium ion, or excuse me, solid pure sodium is not there. We've got inert cathodes. Chlorine gas is not there. We have chloride ions. So the only things that are here to react are the sodium ion itself and the chloride ion itself. So the sodium, even though it's unfavorable for it to be reduced, it has to be reduced because I cannot oxidize any sodium solid because I don't have it. It is favorable for us to reduce chlorine gas into chloride ions, but I don't have chlorine gas. I have chloride ions. So I have to oxidize those chloride ions. The only thing in solution is the chloride and the sodium. So I have to take sodium, I have to take chloride, and then I would turn those into solid sodium and solid chlorine. So I can do, or excuse me, gaseous chlorine. When I do that, my sodium, therefore, has to be the oxidation. Excuse me, has to be the reduction. I wasn't looking at that correctly. Has to be the reduction, so it has to be at the cathode. The chloride has to be the oxidation, going from negative up to 0 by losing some electrons. So that has to be my anode. I would use a battery or an outside voltage source to force the electrons to leave here and come over to there. And that would turn my sodium and chloride ions into solid sodium and into chlorine gas. I would take my negative, my reduction potential at my cathode minus my anode reduction potential to get a negative 0.407 volts. We have to put in a lot of voltage for this to happen. If we have a pure molten sample, the nice thing is that the anion will always be oxidized, the cation will always be reduced. And even as we get into more complex samples, we're always thinking about, am I oxidizing my anion or am I reducing my cation? So that's the nice thing that we'll look at that will stay constant, but it's still going to be all about what ions are in solution, what is their reduction potential, and therefore what can